So the McClevity rearrangement in question 6, probably not part of most A-level curricula, and consideration of esters like we're about to do in this question 7, also probably not part of most A-level curricula. Doesn't mean we shouldn't do it. Now I should warn you at the outset, I think this is the hardest question of all the spectroscopy that we have done. So let's see how you do with it, shall we? So favourite collection of esters, C4H8O4. There are 4 esters with that formula that you might remember from previous spectroscopic studies. 2 of them are formate esters and 2 of them are non-formate esters. Now what do I mean by that? Well, an ester is of course what you get when you take an acid fragment plus an alcohol fragment, and so the ester group is CO2. So remove CO2 from there and we're left with 3 carbons and 8 hydrogens that were the R groups of the original acid and alcohol. Now, if we just take one of those hydrogens and put it on the acid carbon, so in other words, we started with formic acid or methanoic acid, well, then the remaining C3H7 were part of the original alcohol. So that was propanol or isopropanol that formed those. Not worried about those in this part of the question. We'll come to those later on. What we're worried about here are the non-formate or the non-methanoate esters. So that's where the C3H8 gets split into a CH3 and a C2H5 groups. Okay, so we can either have it that the ethyl group was part of the original acid. So this is propanoic acid with methanol, or in other words, methyl propanoate. Or we can have it that the methyl group was part of the original acid, so this was ethanoic acid, and the ethyl group was part of the original alcohol, so that's ethanol, or this is ethyl ethanoate. Now let's look at the fragmentation patterns that we would expect from these before we look at the spectra themselves. And of course the big thing with oxygen containing species is breaking the bonds to the oxygen's carbon. So we got bond break there, break there, break there in this particular one. Let's see what we've got. Start off with that one, and we'd have the ethyl fragment, mass of 29, that I hope you're very happy to recognize by now, and then the acylium ion that contains the carbon-oxygen double bond that of course becomes a triple bond, and that has a mass of 59. So I might expect a big mass of peak at 59 for this one. Now let's break this bond here, and when we do that we make the other big acylium ion, CH or CH3, CH2, C triple bond O from this fragment that has a mass of 57. And of course what's left from that is this bit here that has a mass of 31. And then finally breaking here, we'll have the mass of 73 and a mass of 15 for the methyl group that of course is dead boring and we hardly ever see. Let's go over here, and again we've got these fragments here. We're talking about boring old methyls. We're not really going to see that too often, but we will see that nice acylium ion here that's got the mass of 73. Break here to make the other acylium ion. We get this one that has a mass of 43. And continuing on the patterns, there's the residual there with a mass of 45. And then we can break here, which would give us mass of 59 right there. And the remaining ethyl group there, mass of 29. So when we match this up, we're going to have probably a big 73 and a big 43 we would expect in one, big 57, big 59 in the other. See a lot of similar peaks, 73 in both, 29 in both, 59 in both, but hopefully either the 43 that we get from the ethyl ethanoate or the 57 that we get from the methyl propanoate will enable us to identify them properly. But remember, the two acylium pairs, 57, 59, 43, 73. So spectrum G, what do we see here? There's 43 as that base peak. Now remember, the only time we see 43 was associated with that peak there. Okay, so that's a pretty good indication that this one is the ethyl ethanoate, where we're expecting the 43, the 73 much smaller down there, and then if we want to, there's the 29 we're expecting, there's the 45, 59 not there, 61, well, things just weird and so on. But anyway, the base peak of 43 pretty much unambiguously identifies spectrum G as ethyl ethanoate. Let's hope that the other spectrum matches up with our 57 and 59. There's the 57, there's the 59. If you remember, we're expecting that from the two acylium ions associated with this one. So there's the 59, and there's the 57, breaking either this bond for that one or this bond for that one. Other peaks, there's the 31, 73 not there, but that's okay. The 73 was there where we needed it for the acylium ion for the other one. So there we are, the two non-formates assigned. Now, J and K are the two formate esters, peak at 42 in both. Can you explain the presence of this peak? Well, anytime you get something weird associated with acids or acid derivatives, think McClevity rearrangement. So here are the formate esters. Okay, first one there, formate with just the straight propanol. From the McClevity rearrangement, we remove an electron from the lone pair on the oxygen, giving us this radical cation here. Can we make a six-membered ring for that? Absolutely. There's the oxygen, carbon, oxygen there. Call this carbon 1. This carbon 2 there has got a hydrogen on it to make up the sixth member of the ring. And then, of course, the CH3 floating array there. So remember how the split goes. We're going to move the hydrogen over there to the oxygen. We then split at that bond directly across the ring from that, giving us this little species here from that, and then CH2, CH, CH3, which has a mass of 42. So have a look at the other formates. So if this was based on propanol, this was based on isopropanol. Again, make the radical cation there. Now let's see if we can rearrange all these carbons to give us that six-membered ring. And there indeed it is. There's the OCO, and this is C2 right there. This is one of those C3s. Here's the other C3 there, which has a hydrogen on it that can complete the six-membered ring. Make this bond to the OH, break this bond here, fragment it appropriately. And there again is a CH3, CH2, CH2, the CH3, CH, CH2, which has a mass of 42. So 42, both of these from a McClevity rearrangement and the appropriate fragmentation. So which spectrum is which? Might need to assign one, then the other by elimination. So I put the two spectra side by side so that we can look at the peaks appropriately. I apologize that this is therefore going to get a little bit messy before the end, but hopefully not too messy that you miss the points. So anyway, the two formate esters we have, there's the formate, the hydrogen as part of the original acid, and the one based on propanol or isopropanol. In both cases, the molar mass is 88. In neither case was the molecular ion present. That's why I've cut the spectra off before we get to that. Now, first thing is, of course, there's 42 and 42 in both of them. Now, if I look at the rest of the spectra, this here doesn't have a lot of interesting features. There's this peak at 31 that is a strange one associated with formate esters generally that I'm not going to get into. But then over here we have a peak at 43, peak at 45 and a peak at 73, all of which I think are worthy of attention. Now the first thing is 43. What's 43? Where have we seen that before? Well, it's C3H7. Okay. Now both of these, of course, we expect to see a propyl peak coming out, but this one here, when we take it and break it here, the propyl will be a primary carbocation. However, here, if we break it, it would be a secondary carbocation. So therefore, I would not expect to see very much of a propyl peak here at 43, but quite a significant propyl peak here for 43. So I'm going to say that that 43 indicates we've got this one here, because of the presence of this ion, the secondary carbocation. Now, of course, we then got the peak at 45, which is what we have left when we take away 43 from 88. So indeed, that's breaking this bond here, and it's the HCO2 fragment right there. Okay. Now, the fact that that's so high here, and so minuscule, relatively speaking, here, would indicate that what's left when we have that fragmentation should be a nice stable radical, and again a secondary radical, much better than a primary radical. Last one here is 73. Well, 73 from 88 is 15. So in other words, this is what we get when we lose CH3. Well, if we lose CH3 from this ester, we're again left with a primary carbocation. If we lose CH3 from either there or there, then it's going to be a much, much, much nicer species. Okay, so that's, I would claim, is this radical here or the cation here rather than this one. All of which, when put together, would indicate that spectrum J is the isopropyl ester and spectrum K is the straight propyl ester. So hopefully that made sense. A bit sneaky,